Welcome back to my series on quantum spin. Up until this point, we've been thinking about particles, like for example an electron, as being planted at some point in space and having some spin state, which is a vector with, two complex components. However, we haven't addressed how this electron actually, moves around in space. In real life, electrons, they move around, they occupy, different regions of space and they do stuff. So in this video, we're finally going to address particle motion. We're going to look at how electrons move around. In order to do that, we're going to have to introduce, wave functions and Gaussian wave packets and, stuff like that. And we're also going to look pretty deeply into how magnetic fields affect the motion of an electron. So if you have, it turns out that if you have a changing magnetic field, then that electron will feel a force due to that changing magnetic field, depending on its magnetic moment, it'll move around and, stuff like that. So what I want to show you in this video is, how electrons move around and teach you some basic stuff about it. And beyond that, I also want to sort of give you some intuition for how this works. So at some points, I'm not going to be 100% rigorous, but I want to, instead of, being completely rigorous, I want to teach you ways so that you can get an intuitive grasp on electron motion, without having to work out all the details necessarily. So, those are my goals for this video. All right, so let's get started. Okay, so particle motion. And right now, we're going to be ignoring spin, and we'll come back to that a bit later. So, when we want to talk about a particle moving through space, we use something called its wave function, right? So here I'm writing psi of t and x. Right? This is called the wave function of the particle. Here t is some time and x is some position vector, right? So it's just a three-dimensional vector with components, let's say x, y, and z. All right. And then psi, which is a function of t and x, is a complex number, right? So this whole thing is some complex number with a real and an imaginary part. Okay, so if you know this wave function, what does it tell you? Well, the absolute value of psi of t and x squared is the probability density of finding the particle at position x at time t. Okay, so probability density. What is a probability density? Well, let's say you have some position x and you have an infinitesimal cube around it with some infinitesimal volume, let's call it dV. Now, the probability that you find the particle in this infinitesimal volume with volume dV is just the absolute value of psi of t and x squared times dV. So the probability of finding it in this infinitesimal cube is infinitesimal itself. But that's what we mean when we say probability density. Okay. So in particular, that means that if you integrate the absolute value of psi of t and x squared over all of space, right? So you're doing a volume integral over all position variables x. So if you do this integral, this should be equal to 1. And here t is, you can choose any particular time. We're not integrating over time here. So this is the condition you should have if your wave function is properly normalized. And this just means that, the probability of finding your particle anywhere in space, is 1. All right. So the next thing we have to talk about is how this wave function evolves in time. So the wave function evolves in time according to Schrodinger's equation. And what is Schrodinger's equation? Well, it's just I times h bar times the partial derivative of our wave function psi with respect to t equals negative h bar squared over 2m, where m is the mass of our particle. And then here we have the second partial derivative of x plus the second partial derivative with respect to y plus the second partial derivative with respect to z of psi. So this is Schrodinger's equation here. Right, so what is this saying? This is saying that if you know psi of t and x at some particular starting time t, and all values of x at that one time, then you can use this equation to figure out what psi is going to be at all later times, right? Because you can just, say one little tiny infinitesimal time step forward, you can use Schrodinger's equation to figure out what psi of t plus delta t is, based on what you already know at your initial time. Now, you might be looking at this equation, you might say, boy, that looks really bizarre. How did you come up to this stuff? Like, is there any way that this makes sense? And there sort of is something, if you've never seen this before, there's nothing really I can tell you that'll make it seem, totally obvious, because, it's not. But here's one way to think about it. The kinetic energy of a particle, right, classically speaking, is just 1/2 mv squared, right? And using that momentum p equals mv, you can rewrite this as p squared over 2m, right? So in particular, the kinetic energy will be equal to 1/2, or rather 1 over 2m times the momentum in the x direction squared plus the momentum in the y direction squared plus the momentum in the z direction squared. All right. Well, in quantum mechanics, p, momentum, let's say momentum in the x direction, is this crazy looking operator. So it's h bar over I times the partial derivative with respect to x, right? So in particular, px squared is negative h bar squared, and then the second partial derivative with respect to x. So if you, plug this in here and also do it for, y and z, then this is in some sense the kinetic energy of the particle. And you might say, well, wait a second, why is p this weird thing? I'm not going to really get into it right now. At a certain point, I'm just telling you what the rules of the game are. It was pretty hard for people to come up with this for the first time, and this is, in some sense, just, what it is. Okay. Now, there is one very important solution to Schrodinger's equation, right? This is just one particular solution, but it's a really important one. So I'm just going to write this out real quick. Okay, so you might be thinking, whoa, this looks extremely complicated. But it's actually not that complicated. Let me walk you through what's happening here. So, okay, so let's just start from the beginning. So first things first, we got a pi to the negative 3/4 out front. That's just a number, nothing so crazy. Okay, then we have a sigma to the negative 3/2. What's sigma? Well, as we'll see a bit later, sigma should be thought of as the initial position uncertainty of the particle. But right now it's just a number. And then we have c of t to the negative 3/2, right? So as I've written below here, c of t is just some other function I've defined that's equal to 1 plus I times h bar times t over m times sigma squared. Now m, as I've said previously, is just the mass of our particle. So okay, then we have the exponential function, right? So that's just notation. So for instance, exp of x is just equal to e to the x. It's just notation. And then we have negative 1/2 and then x squared over sigma squared times c of t plus I times p dot x, where here p, this is just a vector with three components, px, py, and pz. And I know previously I said that px was equal to h bar over I times partial x. That's not true here. Here these really are just three real numbers that we're putting into our solutions. So I don't want to confuse you. These are just three real numbers. Okay. And then we have minus I times p squared over 2m times t over h bar, and then over c of t again. Okay, so you can see there are three parameters that go into this. There's sigma, which is as we'll see, the position uncertainty. There is the mass m, and there are the momentum vector. Okay. So when I say that this function is a solution to Schrodinger's equation, all I mean is that if you were to take this function, psi of t and x, and you were to plug it in here and here, you would, you were to compute the left-hand side of the equation and you were to compute the right-hand side of the equation, you would find that this equation holds. So that's just what I mean when I say this is a solution. I'm not going to, do out all the, derivatives here, but, you could do it for yourself if you want. You would find that this holds. Okay. So oops. Now, the next thing you might wonder is, what is the absolute value of psi of t and x squared, right? Because that's the probability density of where the particle is. So I'm just going to write that out really quick right now. So, okay, there are a lot of things to say about this. The first is that if you integrate the absolute value of this wave function squared, if you do a volume integral over all positions, you will indeed find that this is equal to 1. I'm not going to do it here, but that is the case. So that's the first thing. The next thing is, what general shape does this function have? Well, you can see that the only way it depends on x, right, is right here. And you can see that the function will be a maximum when x equals p times t over m. So in other words, I can't draw it in all 3 dimensions, but I'll just sort of draw it on 1 dimension here, let's just say x. What this will look like is it will look like a bump that is maximum where x equals pt over m, right? So here I'm graphing the absolute value of psi squared. And like I said, I'm only doing it on 1 dimension just because I can't do, x, y, and z, on the screen. But okay, so this is actually called a Gaussian, the exact shape. Furthermore, the width of this Gaussian, right, is going to be, it's going to be the square root of this thing right here. That's what the width of the Gaussian is going to be. So the width is equal to the square root of sigma squared plus h bar times t over sigma times m squared. So at t equals 0, the width is going to be just equal to sigma, right? So that's what I meant when I said sigma is the initial width, the initial uncertainty of the position of the particle. Furthermore, actually, as t gets really big, so as t goes to infinity, the width becomes just h bar times t over sigma times m. So, just something I thought I'd mention. But, okay, it's kind of hard to get too much of a sense for this just by drawing these pictures. So now I want to show you something pretty cool. Okay, so here I have transported us into the land of Wolfram Mathematica, which is a very powerful piece of software which I get for free through my university. Now, what I've done here is I've made a little animation, and I'll press play in a bit, but what this animation is going to show is how this Gaussian wave packet evolves in time. Now up here is all of the code I've written to make this little animation. So let's just take a quick look. Here we can see that I've made a function, psi of x and t. I'm only doing it once again in 1 dimension, just x instead of x, y, and z, just because it's easier to show. Here we can see I have, sigma, h bar, the mass m, the momentum in the x direction p, which I've just set to some random numbers here. I also have this other variable ts, which is sort of like t scaling. I just wanted to scale up how fast the animation goes because I thought it seemed kind of slow, so I just wanted to make it go a little faster. And so what we have here is we animate how the wave function evolves. Now I'm really graphing 3 things. I'm graphing the absolute value of the wave function in black, I'm graphing the real part of the wave function in blue, and I'm graphing the imaginary part in red. So when I press this play button, what's going to happen is this Gaussian wave packet is going to move to the right and it's going to get wider. Now, unfortunately, because of my recording software, there's going to be a bit of lag. It's going to be choppy. So well, let's just press play and see what happens. Yeah, so you can see the animation is a little bit choppy, but I have downloaded this animation as a movie file, and I will now play that so you can see what it looks like when everything is moving smoothly. Now, there are a few things I want you to notice here. The first is that while the envelope of this wave function, the black line, the absolute value of the wave function, is only moving to the right and getting wider, the real and imaginary parts are oscillating rapidly, and that's generally what it's going to look like. Now, if all you're interested in is the position of the particle, you'll never know about this. But it's sort of important for how the wave function evolves in time. It turns out that the phase of the wave function, the angle of the complex number, what makes the real and imaginary part oscillate, is what encodes the information of the velocity of the wave function. So the higher the velocity, the higher the frequency of the oscillation is. Now, because I have the code up here, if you want to play around with the numbers and you have access to Mathematica, you can just type this into Mathematica and you can play around with it for yourself. I should say that I kept encountering this weird bug where it wouldn't work, but I saw online that if you go to Edit and you go to, where is it? Oh, Preferences. There is this, wait for Preferences. Whoops. Yeah, here's Preferences. There's this box that was checked called Show Suggestions Bar after last output that's usually checked. And if you just go ahead and uncheck that, that made it work. So I don't know why that happened, but I'm just letting you know that's what you can do if you get the same error I did. Okay, so now that we have talked a bit about how particle motion works in quantum mechanics, when you're not taking spin into account, now we're going to talk about how it works when your particle has spin. So particle motion with spin. So now we're going to describe a particle which moves in space and also has spin. So when we weren't taking spin into account, the state that described the particle was just this wave function, psi of t and x. Now, how do we then describe spin, on top of this? Well, remember that, when you're just thinking about spin, you're not thinking about particle motion. Your state is just described by a two-dimensional vector, right? So this is how you describe your state when you have spin but no motion, and this is how you describe your state when you have motion but no spin. So how do you think, you put the two together? Well, the way you put the two together is that you now have two wave functions. Let's call them psi spin up and psi spin down. Two different functions, both functions of t and x, and we can write them in a two-dimensional vector like this. So state is a two-dimensional vector of functions, where each of these functions, output a complex number when you put in some time and some position. Now, what is the interpretation of each of these functions? Well, let's say, the absolute value of psi spin up evaluated at some t and x, right? So take the absolute value squared. This is the probability density of finding your particle at position x at time t, spin up with respect to the z-axis. Right, so that's what the absolute value squared of psi of spin up is. It's the probability density that you find your particle at some position x at some time t, and that when you find your particle, it's also going to be a spin up with respect to the z-axis. And likewise, the absolute value of psi spin down at some t and x squared is the same exact thing, but spin down with respect to the z-axis. Now, if you want to know what the probability density of finding it at some particular position is with spin up in some other axis, like for example, spin up in the x-axis or spin up in the y-axis or any arbitrary axis, you have to create a linear combination of psi spin up and psi spin down, just the same way we do for, just the two-dimensional complex vector, right? So this state, for instance, has a 100% chance to be found spin up in the x direction, and likewise, the absolute value of 1 over root 2 times psi spin up at t and x plus 1 over root 2 times psi spin down at t and x all squared. This is the probability density that you find your particle, at position x at time t, spin up in the x direction. Right? So that's how that works. All right. Hopefully that didn't confuse you too much. Okay. So whenever we have some notion of a state in quantum mechanics, we have to have some sort of normalization condition. So for example, when we were just talking about a particle without any spin, we had to have that the absolute value of psi of t and x squared integrated over all of space. We had to have that this was equal to 1, and that was our normalization condition. And it just meant that the probability of finding it anywhere has to be equal to 1. So what is the normalization condition here? Here, the normalization condition is just that if you integrate the absolute value of the spin up function squared plus the absolute value of the spin down function squared over all of space, right? So you were fixing time and integrating over all spatial positions. This is what has to be equal to 1. And then this is our normalization condition. This, is just saying that the probability of finding the particle anywhere in space with any particular spin, either spin up or spin down, that has to be equal to 1. So that's a normalization condition. Okay, so in quantum mechanics, there's always only two things you ever need to know. You need to know what your states are, and you need to know how your states evolve in time. So here I've just described to you what the states are when you want to describe a particle that moves around in space and has spin. And now all I need to do is tell you how this state evolves in time. And specifically what I'm interested in is time evolution in electromagnetic field. Right, so when we have our particle with spin and we place it in an electromagnetic field, how does that state evolve? So I'm going to write out the equation, and it's pretty long. So here I go. All right, now clearly this is a very complicated expression, so I have to break down what everything means for you here. So right off the bat, we have I times h bar times d dt of our state. This is how time evolution equations always start in quantum mechanics. And then we have this big thing here. Now this big thing here is in some sense a 2 by 2 matrix. And it's a little more complicated than that, but it's basically a 2 by 2 matrix. And you can see that here we have I, where this I is the identity matrix 1, 0, 0, 1. Right? So this is the identity matrix. And we have this weird thing out front here. But this weird thing is just multiplying the identity matrix. So we'll get to the weird thing in a second. But here you can see we have B dot the sigma, the Pauli matrices. So remember that this sigma with a vector is just a vector of matrices, sigma sub x, sigma sub y, and sigma sub z. This is just some notation where sigma sub x is the first Pauli matrix 0, 1, 1, 0. Sigma sub y is the second Pauli matrix 0, negative I, 0. And sigma sub z is the third Pauli matrix 1, 0, 0, negative 1. So B dot the sigma vector, is just borrowing notation from the regular dot product. So, for instance, right, so B dot sigma equals Bx times sigma x plus By times sigma y plus Bz times sigma z. So this whole thing, is just a 2 by 2 matrix here. So here we have a 2 by 2 matrix, and here we have Q over 2m times h bar. Now Q is the charge of our particle. So if we have, say, an electron, then Q equals negative E, where E is the elementary charge. So that's Q. M is the mass of our particle. And here we can see that this term right here, B dot sigma, this is going to be, some sort of 2 by 2 matrix that mixes up the two components of this vector here. So this part mixes up the two components of our vector. So the time derivative of the spin-up function, or the spin-up wave function, is going to depend partially on the spin-down wave function, right? Because this is going to, mix it up. And the time derivative of the spin-down function is going to depend partially on the spin-up function. So this term kind of couples the two components together. This term doesn't do that, right? Because this is just a identity matrix, and that doesn't couple the two components of the vectors together. Now, if you've seen some of my previous videos, this term might look familiar to you, because this looks an awful lot like negative mu dot b, where b is the magnetic field and mu is the magnetic moment of your particle. Where here we've approximated the g factor equal to 2, but if you don't know what the g factor is, don't worry about that. But yeah, in my previous videos where I was interested in how the spin of a particle changed in time when the particle was placed in an external magnetic field, we were just really looking at this term, and we weren't interested in the motion of the particle. We were just interested in how the spin of the particle changed. So you can see that this term is just one piece of the broader equation, right? So we were only studying earlier just this one piece, but now we're looking at the whole equation. Okay, so now it's finally time to look at this crazy term, right? So if this term governs how the spin of the particle changes in the external magnetic field, this term governs how the particle moves in an external electromagnetic field. So here we have, to start things off, 1 over 2m, where m is the mass of the particle. Then we got h bar over I times del, right, where del, is just this vector with components of partial derivatives in the x, y, and z directions, right? And then we got minus q, where q is the charge of the particle, times a. Now you might not have ever seen this thing a before. A is something called the magnetic vector potential. And what defines A is that the curl of A, so del cross A, this is the curl of A, this is equal to the magnetic field B. So this is what I mean when I say that A is the magnetic vector potential. It satisfies this equation. If you've never seen this before, don't worry about it too much. But basically the magnetic field has some thing that kind of acts as its potential, but the potential isn't a scalar function, it's a vector, and that's what A is. Okay, so that's A. And then here, we then have plus Q times phi. Now phi is the just the regular old electric potential. So if you've ever seen, the equation that the electric field is equal to negative the gradient of phi. Yep, that's this phi. That's the potential that the electric field is a gradient of. Or rather, negative the gradient of. Now actually, this equation, which you may have seen, isn't actually perfectly correct. You actually have to then add this other part to the equation, which is partial A over partial T. Yeah, this equation is completely correct. If you don't have this, it won't always be correct. But when you're learning about it for the first time, this will get you far. Now, some of you might be wondering, how can you have this crazy thing here multiplying the identity matrix I? Like, what does that mean? And I'll spell it out for you in a simple example. Let's just say we had del squared times I, and this was acting on our vector of functions, the spin up function and the spin down function, right? So this would then just be equal to, del squared times the identity matrix 1, 0, 0, 1, and then the spin up and spin down functions here. And then here we're thinking of del squared as in some sense a scalar which multiplies this matrix. So this would then be equal to the following matrix. Here we have del squared 0, 0, del squared. And here we have the spin up and spin down functions, and then just multiplying this matrix, by this vector, we then get the vector of functions, del squared times the spin up function, and then del squared acting on the spin down function. Remember that del squared is equal to the second partial derivative with respect to x plus the second partial derivative with respect to y plus the second partial derivative with respect to z, right? So that's how this thing acts. And here A is just a vector, or really a vector field, right? Because, A depends on t and x, right? See, both phi and A depend on t and x in general. So, those would just be functions, and those also just, multiply the identity matrix in the way you would expect. So, okay, that's how you can have, crazy stuff multiplying the identity matrix and what that means when you write it out. Okay. All right, now let's clear a bit of this off. Now, the last thing I want to talk about, to fully explain everything, is what it means that we have this thing here and then it's getting squared. Like what does that mean? That's the final thing I have to say. Okay, so let me just write this out here. So h bar over I times del minus q times a squared, and then we have the identity matrix, and then we have our two-component vector of wave functions here. So I'm going to write this out a little more fully. So this is h bar over I times del minus q times a, right? I've written it the first time, and now I'm going to write it a second time. That's what the square is instructing me to do. And then I'm not going to write the identity matrix because there's not really any point to doing that. And then I'm going to write here my two-component vector of wave functions. And then finally, I actually need to have a little dot here. So usually when you have like a vector and then you write the vector squared, that's really just notation, which means the vector, the vector dot itself. And that's the same thing that's going on here. So what do we have here? Well, first off, the dot means that this is really three terms, an x term, a y term, and a z term. So for instance, del dot del, well, I mean, I kind of wrote that earlier when I said, del squared, that's equal to, that's equal to this thing, for instance. Okay, whatever. So, yeah. Right, so what is this really saying? This is saying that first you act with this operator on this vector, right? And that's going to get you some result. And then with this result, you act with this whole thing on this. So that's what the square means. It means first you act with this on this, and then with the whole result of that, then you act with this on this. And there are going to be three terms like that, one for the x component of this three-dimensional vector, one for the y, and one for the z. Now in particular, there are going to be cross terms where the del is going to hit the a. So that's pretty confusing. So in general, this is going to be, if you really wanted to write this out in all the components and everything, that would be pretty confusing to write down. So hence why we just write squared here. It's very compact notation. Okay, so that's what the square means. It's pretty confusing. Okay, so now that I've just explained to you what all the notation here means, what does this term really accomplish? What does this term really do? Well, what it does is, if you imagine that you have a little wave packet, this term is basically responsible for the magnetic force, in the sense that if this wave packet is traveling with roughly some velocity and it's in an external magnetic field, then you have the Lorentz force, F equals QV cross B, right? This is true classically. Roughly speaking, this is also going to be true quantum mechanically, in that the position of this wave packet is going to, quote unquote, feel this force, and the average position is going to move like the classical particle would. It's going to, the average position is going to feel the force. And right, so this whole situation here is responsible for the magnetic force. Oops. And this is responsible for the electric force. Right, so this is the magnetic force, but then there's also the electric force, Q times the electric field E. So in general, this is obviously an extremely complicated expression. But what I'm claiming, and I haven't proved this to you at all, I'm just claiming this out of nowhere. What I'm claiming is that if you just think about having little wave packets like this, right, little Gaussian bumps, you can sort of think about the Gaussian bump feeling the regular classical forces and the peak, the average position of the Gaussian bump, moving accordingly. Okay, so this is clearly a pretty important equation, very complicated equation. But I haven't said what the name of the equation is yet. This equation is called the Pauli equation. The equation that governs how a spin 1/2 particle moves in an electromagnetic field. Now, there's one final thing I want to talk about, which is this term. Now, earlier I said this term is responsible for how the spin of the particle changes. But you can also think about this term as giving rise to a force too. Now, what is that force? Now, this force is going to be a force on the magnetic moment. And classically, this force is equal to the gradient of mu dot b. So in an earlier video, I discussed how when you have a magnetic field which is constant throughout all of space, there's going to be no net force on the particle. Now, there can be a torque on the particle, which makes the spin process, but there's not going to be any net force on the particle. But if the magnetic field B varies in space, then there is going to be actually a net force on the particle. See, if B is constant, then this thing right here is also going to be constant, and then the nabla of a constant is 0. But yeah, a lot of you might not be familiar with this force. I certainly wasn't too familiar with it for a while. I had to, say, okay, wait, what's the deal with this force? But this is the force I wanted to spend the rest of the video basically talking about. So actually, I'm only going to, for the rest of this video, only talk about classical mechanics. And I'm going to show how this magnetic moment force arises classically. So I want you to understand the way I have structured this lecture here, right? I spent the first part of the video talking about wave packets, and I wanted to build intuition for how these little wave packets, how they operate quantum mechanically, but also how you can use classical intuition to think about them. In some sense, you can kind of think about wave packets in some fuzzy senses. You have a particle which is, sort of located in some position. There's some position uncertainty, and it's going to spread out in time. But the position of that wave packet, the average position, can, feel forces, as I've discussed, and by sort of using this classical intuition of forces on a particle, we can get a very qualitative sense for how quantum mechanical particles are going to evolve in time. And if you have a good sense of the classical mechanics, you can get a decent sense for the quantum mechanics if you're only interested in wave packets. So I'm sort of assuming that most of you are familiar with the Lorentz force and the regular old electric force. But I kind of think a lot of you don't really know too much about this magnetic moment force, the force exerted on a particle when it has a magnetic moment. So for the rest of the video, I'm just going to talk about this classical case just so you get some appreciation for this force. But in reality, I'm kind of really interested in what happens to these wave packets. But because I spent so long drawing an analogy between wave packets and classical particles, it should make sense to you sort of what these things have to do with each other. But okay, now we're going to transition, and I'm going to derive where this force comes from classically. All right, so now we're going to do the F equals del of mu dot B, i.e. the force on a magnetic moment derivation. Now, before we get into the math, let's just see if we can understand this equation qualitatively. So let's say we have a loop of current, which is our prototypical example of something with a magnetic moment, and we're placing it in an external magnetic field. So let's say that the magnetic field is stronger, down here, and it's weaker up here. So the field lines will kind of look like this. They'll kind of bend outwards like this. So remember that the strength of a magnetic field is proportional to the density of field lines. So because the field lines are all, close together at the bottom, but then they're further apart, up top in this region, the magnetic field is, stronger down here and weaker up here. So the magnetic field is changing at the location of the current loop. And remember that this is an external magnetic field, not the one induced by the current loop. Now, the question I want to ask is, what is the direction of the force that this changing magnetic field will make on the wire? So to answer this question, we have to use the Lorentz force law that F equals Q V cross B. And if we think about this current loop as being some circulating positive charge, in real life, in a real wire, it would be circulating negative charge, but let's just think of it as positive charge for simplicity. Then at this rightmost point on the wire, the velocity vector of this positive charge would be going into the page like that. While on this leftmost point, the velocity vector would be coming out of the page like that. Meanwhile, at these 2 points, the magnetic field would be sort of pointed at an angle. So on the rightmost point, it would be pointed like that. And on the leftmost point, it would be pointed like that. So this is where the magnetic field is pointing. Now, in order to figure out the direction of the force at these 2 points, we have to use the right hand rule. So now I'm taking out my right hand and I'm going V cross B. And on the right side, I'm getting that the force is going to go in this direction, like that. On the left side, I'm getting that the force is going in this direction. So if we think about summing up the forces on every part of the wire, we're going to get that the net force on this wire is going to be pointed downwards. So this is going to be the direction of the net force, like that. So we can see that in this example, because the field lines are kind of splaying outwards like I've drawn here, the current loop feels a downwards force. So we can therefore see that when magnetic moments are placed in magnetic fields which are varying, from one point in space to the next, they're going to feel some overall net force. So now we're going to quantitatively derive, the expression for that net force. All right. So in order to do this quantitatively, we're going to make a coordinate system. So here's my coordinate system. Here we have x, y, and z. And now we're going to consider a square loop of current instead of a circular loop. So this is a square loop of current. The very middle, I will make the origin, so 0, 0, 0. And for this loop of current, we have, the charge flowing in this direction. So let's say the total charge that's flowing around this, this loop is a charge of q. Now let's also say that the velocity of the charges is what I'll call v, and the length of each side of this little square is going to be L. So L. Now we can also write this in terms of the current, right? Here we have Q, V, and L. But we can write the current going around the wire. That's going to be equal to the linear charge density times the velocity. So linear charge density is going to be Q over, 4L. See, because there's a charge of Q and the total length of this wire is 4 times L. Then we have to multiply that by V. So this is the current going around the wire. And we'll also just write that the area of the square, the area, equals L squared. So first things first, let's just label the velocity of the charge in each segment of this square loop of wire. So for this bottom segment here, v, the velocity v, is equal to 0 v 0. Now for this right segment, the vector v is equal to negative v 0 0. For this top component, it's going to be 0 negative v 0. And then for this left part, it's going to be v 0 0. Now the next thing we have to label is what the magnetic field is on each of these 4 segments of wire. So remember that the magnetic field is a vector field. So for every point in space, the magnetic field, it gives you some vector. And we're interested in, the case where this magnetic field, changes from place to place. It's varying over space. But here's the thing. We actually are only interested in this problem in the limit that this square becomes very small. So we're sort of imagining that the length of this wire L, we're imagining that this is very small because eventually we're interested in an electron, and an electron is very small. So over the scale of the size of this wire, the magnetic field is varying, but not that much. So what that means is that we can find the value of the magnetic field on each of these 4 segments of wire by doing a Taylor expansion. So for instance, B at, let's say, the location of L over 2, comma, 0, 0. This is going to approximately be equal to the magnetic field, so B 0, 0, 0, plus L over 2, and then partial x b, and then this derivative evaluated at the origin, so 0, 0, 0. So this is a first order Taylor expansion, and here we're assuming that L is small and B isn't going to vary much over the length scale of L. Now this means that if we know what the magnetic field vector is in the middle, let's say, well, let's call that B naught. So what I have written here is B00. Let's call that, B naught, so B0. So the magnetic field in the center has a value of B0. And on this, let's say this top component of wire here. So on this top component of wire, which has an x-coordinate of negative L over 2, here, for this top component of wire, we can take that B is approximately equal to, let's say equal to B naught, and then minus L over 2, right, because here x is minus L over 2, and then partial x times B. So you might be saying, well, wait a second, that's what the value of the magnetic field is at this point, this point being negative L over 2, 0, 0. But actually, because L is small, we can take that to be the value of the magnetic field on this whole segment. And the reason for that is because if we figure out what the value of the magnetic field is here, we can do another Taylor expansion to figure out what it is over the whole, for any point on this segment. But that'll be another order higher in L. So that'll actually be second order in L. And we only want to keep the first order in L here. We don't, because L is small, we're interested in stuff of order L, but we're not interested in stuff of order L squared. So to order in L, we can just take this point on the wire and just, figure out what the magnetic field is at this point, but not worry about, what it is at, this point and this point, because, to leading order in L, it'll be the same. All right, so let me just get rid of this. And let's finish labeling what B is on each of the, the other three segments of wire. So at this bottom segment, we have that B is B naught, and then here we have plus L over 2, partial x B. So yeah, the derivative of B, at evaluated at the origin. So then on this right component, we have B equals B naught, and then here we have minus L over 2 partial y B, and then on the left we have B equals B naught oh, wait a second, this should have been a plus y, sorry. And then this should be a minus L over 2 partial yb. Okay, so finally, now that we've figured out what V and B is for all of these four segments, we can now figure out what the force is on each of these four segments. So we're going to do this using the Lorentz force law. So F equals Q V cross B. So on each of these four segments, this charge Q, little q, that's going to be big Q over 4 because that's 1/4 of the wire. And for the B as a vector, note that, for instance, let's say partial xb, that's just a vector with components of partial x bx, partial x by, and partial x bz. So yeah, so this is just a vector that we can plug in. So in order to do this part, you just, for each of these four segments, plug these two things into the Lorentz force law. And to do that, you have to look up the formula for the cross product and everything. But yeah, I'll just write the answer here. So let's start with this bottom one. So here we have All right, so this is the result of doing this cross product for all four of the segments. We just have to use the cross product formula. I have it up here, so if you want to do it yourself, you can check against my work here. And now that we've gone through and done all that, it's just it just takes a little bit of time, but it's nothing hard about it. Now we're going to add up all of these forces and see what the net force is. Well, actually, let's just sort of clean up the screen a bit, so just so it's visually easier to see, what we were looking at. Now we don't need V and B anymore. All right. Very cool. And bring this up here, I guess. Actually, yeah, let's delete this and all right. Okay, so now we're going to sum up all these forces and see what the net force is. So F net equals, so right out front we still have QV over 4. And now for the first component, well, okay, so let's see here. So this segment has something in the first component, and so does this one, but these two right here have 0 in the first component, so those don't affect it. And now note that here we have B naught Z and negative B naught Z. So those cancel out. So that cancels out and that cancels out. But crucially, the term that's first order in L, those add, right? So this is actually the same as this one. So these will add together, right? So this is why we had to keep everything to the next leading order in L, because what you would have thought was the leading term, those cancel out to 0. So in the first component we have L, and then partial x bz. Okay, great. Now let's look at the y component. So for the top and the bottom segments of y are now, the y component is 0, so that doesn't matter. And now it's the left and the right for which the y component isn't 0. And just like before, with this leading piece, b naught sub z, that gets canceled out because, see, one of them is negative, one of them is positive, so those cancel out. And then it's the term which is proportional in L, which, adds. So here, for F net and the y component, we have L, and then partial y bz. Now finally, let's look at the z component. And the z component's a little different because here we can see that every piece of wire has a non-zero z component. So, okay, let's start with the b naught x part. So here we can see that once again, the top and the bottom ones cancel out, and for b naught sub y, the right and left ones get canceled out. So now what we're left with is once again the thing proportional to L. But here notice that we have actually a few terms. So here we have negative L over 2 partial x bx, and that adds with this one right here. And then here we have negative L over 2 partial y by, and that adds with this one right here. So overall, we get negative L partial x bx, and then minus L partial y by. So we can see that the z component the z component looks different from the x and the y components here. Okay, so actually now let's clean up some of this now, so we can just focus on fnet. So, oops. All right. Very cool. So, okay. It looks pretty weird how this z component looks different from the x and the y components, right? Like, here we have L partial x bz and then L partial y bz. So you might expect that this thing should have been L partial z bz, right? Like, this is what you might have expected to get here, but we didn't. But actually, it turns out that these two things are equal, and they're equal for an interesting reason. So you may or may not know that one of the laws, Maxwell's laws for electromagnetism, is that del dot B equals 0. In other words, the divergence of the magnetic field is 0. This is also the statement that there are no magnetic monopoles. And if we write that out a little bit more explicitly, that's partial x bx plus partial y by plus partial z bz equals 0. This is one of Maxwell's laws. So using this equation, we can actually directly see that, this thing that we got is actually equal to L partial z bz. So interestingly enough, this law that we're trying to derive up here actually crucially depends on the fact that the magnetic field is divergenceless. There's this constraint on B. If this wasn't the case, then this law wouldn't be true. But okay. So now that we found a way to rewrite this component here, let's just put it up there. All right, very cool. Okay. Now we've almost finished the job, but we just gotta rewrite a few things. So if I just bring all these, symbols up here, notice that the current I, now we're thinking about the current again. So the current I times the area A, that's equal to, well, QV over 4L times L squared. That's equal to QV L over 4. And then notice that QVL over 4 is exactly, what we're seeing right here in our equation for Fnet. So we can rewrite this as Fnet equals I times A, and then times the vector with components partial x bz, partial y bz, and partial z bz. Now, the next thing we're going to do to clean this up a little bit more is to remember what our magnetic moment vector is. So for a little loop of wire, our magnetic moment vector is going to have the magnitude of the current I times the area A in the direction normal to this loop of wire. So that means that it's going to have components of 0, 0, and I times A. So therefore, we can also write mu dot B, and that's just going to be equal to I times A and then times BZ. the component in the z direction. So notice then that we have here I times a, and then times bz in all these places. But we also have, the derivatives partial x, partial y, and partial z out front. So we can write this as equal to partial x acting on the number mu dot b, right? So you see, okay, so here's kind of the interesting thing. Mu is a constant vector. It has this component I times a. Now this isn't, I and a don't, depend on x, y, and z, x, y, and z, like the coordinate in space. But b, which is a vector field, does depend on x, y, and z. So this should be thought of, mu dot b, this should be thought of as a function of x, y, and z. It's a scalar function. It just outputs a number, right? Because mu dot b, that's a scalar. And then this gets differentiated, by x here. So yeah, so that's the first component. Just actually copy this. So we have partial x mu dot b, partial y mu dot b, and partial z mu dot b. So now, finally, for the last step, we can immediately see that this is just equal to the gradient of the function mu dot b. And this is the result that we have been, that we've been trying to derive this whole time, right? So see up here, this was the result we've been trying to derive this whole time. Okay, so now let's clear some of this off. And let's talk about the generalization of this law. So far, we have only derived this law for this square loop of current, right? However, this law would also be true for an arbitrarily shaped loop of wire with a current going around it. And to see why this is the case, imagine making a grid of tiny little squares inside of this wire. And imagine that you had a current of I going around each tiny little square loop. Now, if you think about the loop and this little square and the little square next to it, you sort of put these two, you sort of draw the arrows of the currents, you can notice that the currents actually cancel out, where the squares overlap. And this will be true for all the little squares except for the ones in the boundary. So overall, if you add up, all the little squares together, you just get, one current going around the boundary of the wire. But the important thing is that the areas of all these little squares will add up, and therefore these magnetic moment vectors will all add up. Not only that, but the net forces on all these little squares will also add up. So therefore you can see, by the linearity of this law, that if it's true for this little tiny square, it's got to be true for, any shaped wire. So, okay. Now what about an electron? Usually we think of an electron as a charged spinning sphere. When we think about it classically, so it's a charged spinning sphere with a constant charge density throughout the sphere. And it's also spinning, rotating. Now, it turns out that this law here also applies to a charged spinning sphere. Now, why is that? Well, if you think about what a charged spinning sphere is, you can think about it as actually being comprised of a bunch of charged spinning rings. And, charged spinning rings have some current going through them. So you can think about the charged spinning sphere as being made up of a bunch of little loops of current. Now, importantly, you have to have that the charge to mass ratio is constant throughout the sphere. And I'm not going to go through the details, but I went through it extensively in my 4th video on quantum spin, showing that when the charge to mass ratio is constant throughout the sphere, all the little magnetic moment vectors, add up in the way you want them to. But, the point is that this law is true for the little tiny square, and using a few extra little steps, you can generalize it to the charged spinning sphere, which is how we think of our electron. So yes, the point is that we have essentially derived the force law, not just for the square, but for an electron. So, okay, that's pretty interesting. The next thing I want to show you is a much quicker derivation of this law right here. So this took us, a lot of, sweat to prove, but there's a simpler way to prove it, and I just thought I would share this with you. So some of you may be familiar with the equation that force F is equal to negative the gradient of the potential energy U, right? So, oftentimes we think about this in the context of, say, maybe gravity. You can have U equals mg y, and then, you take the negative gradient of this and you get the force of gravity. Let's say, U is the potential energy in a gravitational field. But for us, for a magnetic moment in an external magnetic field, U is equal to negative mu dot B, right? The potential energy of this, of this magnetic moment depends on the value of the magnetic field at the location of our little magnetic moment. So therefore, if we just plug in this value of U into this equation here, we just get it's equal to the gradient of mu dot B, right? Which is exactly what we got here. So yeah, there's a very simple way to prove this. But the thing is that I like to show why this equation is true by using the Lorentz force law on all the components and seeing it directly. So even though this way is really simple, I kind of like the harder way just because you can see all the components for yourself and how it comes out. Okay, so the final thing I want to do is tie together everything we've discussed in this video, the motion of a quantum particle and the force on a magnetic moment from a magnetic field, and tie it together with a really important example, which I'm going to talk a lot about in the next video. So if you have some sort of particle emitter that emits a particle with spin, and you have some sort of zone, I'll just denote this zone with this box, and in this zone you have a changing magnetic field, created by some sort of instrument, some sort of device, which we don't have to worry about right now. But in this zone, let's say that the z component of the magnetic field is changing with height. So if this particle emitter, emits some particle, then depending on whether the particle is spin up or spin down, from this force law we've just derived, the particle will either be deflected up or be deflected down in this zone with a changing magnetic field. And then afterwards, particle moves on, and you could, for instance, have a back wall that detects the particle hits the back wall, and you can see where the particle hit. Okay, so this is a very important historical experiment. It's called the Stern Gerlach experiment. And what I wanted to convey to you is how this experiment makes sense quantum mechanically. So in the first part of this video, I spent a lot of time talking about wave packets, right? So, have little wave packets which travel with some velocity, And the important thing to note is that if you just think about the position of the particle as being like the average position of this wave packet, right? Then this wave packet will get deflected depending on whether or not the particle is spin up or spin down. More specifically, we have that the state is given by two wave functions, one spin up wave function and one spin down wave function. So the spin up wave function, for instance, will get deflected upwards, and the spin down wave function will get deflected downwards. So the whole point of this video has been trying to explain to you how to think about this process qualitatively. Earlier in this video, I wrote out for you the Pauli equation, and that Pauli equation was really complicated. And if you were to exactly solve for the solutions analytically, they would also look very complicated. But sometimes it's important to sort of know how something behaves without having to solve for it exactly analytically. You want to approximately understand what's basically going on. So in quantum mechanics, you can often understand what's going on with classical intuition by making wave packets and then figuring out classically like what the trajectory of these wave packets would be. So that's exactly what we've done here, and it's basically all you need to know in order to understand how the Stern Gerlach experiment works. Okay, this concludes the video. Thank you so much for watching. I know it's been a long one, but we've covered a lot of ground, I hope. We started out not knowing at all how electrons moved in space, and now we know, I think, quite a bit about how they move around in space. So I think that's quite a bit of an accomplishment. My next video, which will build directly off of this one, will look really in depth into the quantum measurement process, and will answer a lot of questions that I think people have about the quantum measurement process that aren't usually addressed in introductory quantum mechanics classes. Questions of how does observation change a state and all that. Because we now understand the Stern Gerlach experiment pretty well, I'll talk more about it in the next video too, but now that we can understand it pretty well, we can use this measurement process as a springboard to understand stuff about quantum measurement in general. So I think that'll be pretty interesting.